If you are a bit familiar with machine learning, you have probably heard the term overfitting. But what does that intuitively mean? And more importantly, what does that actually mean in a mathematical sense? To understand the latter, we will introduce some machine learning fundamentals, namely what the bias and the variance are. But first, what do machine learning models want to achieve intuitively? One application is, for example, that they want to learn how to differentiate between dogs and cats. They learn how to do that because we give them example images and tell them what a dog is and what a cat is. For a dog, for example, it learns that they are big and fluffy and cute. And cats are smallish animals with pointy ears and whiskers. The model might have learned to differentiate perfectly those images we have shown it, but once we give it a new image, one that it has never seen before, it might struggle or just fail. Or in other words, we can say that the model overfitted and generalizes poorly. What do machine learning models want to achieve mathematically? They want to build a mathematical equation that perfectly represents the real relationship between data points. We want to be able to then put in some new data x and have it predict the correct y value. But what is the best graph or model that represents the real relationship, that is the best fit to the data we can provide for training? By the way, I will use graph and model basically as synonyms. So, is it one of the simplest models, a straight line? What if we rotate the line a bit? Or is it something like this, or this, or this, or this very complex graph? Well, we can all see that the straight line is trash. But let's look at this complex graph or model. Let's call it Model A. It looks kind of weird. We have a feeling that this isn't really the right graph, but it hits every data point perfectly. Terminology time. How well the graph or model fits the data is called bias. Our Model A has zero bias, so it fits the data it knows or that we have trained it with perfectly. Model B, on the other hand, does not perfectly fit the data. The bias is fairly high. And to get back to this useless model, does it have a high or low bias? Correct, a very high bias. We could end this video here and say, well, our model is perfect, it hits every data point we have. But as mentioned, the point of a machine learning model is to be able to predict new, previously unseen data points, new observations, new inputs, according to what it has learned during training. And our zero bias model knows every detail about the dogs it has seen, but once a new data point has to be predicted, one that isn't all too similar to what it has seen, it is absolutely lost. In fact, this failure is even more evident and consistent when looking at multiple different unseen inputs we want to test our model with. It might have perfectly fitted the training data, but by doing so, it is way too weird and complex to be able to predict new data. So again, it generalizes very poorly. This property is called variance. It basically quantifies how much the learned model fails on the testing data, or it measures the scatter around the estimated graph. Our model with a relatively high bias does nevertheless have some variance, but it is still less than the variance of the overly complex model. Intuitively, you can see it should perform better and it somehow looks like it fits the data better. So we realize that with increasing model complexity, the bias does shrink. The model fits the training data better and better. But what also happens with increasing model complexity is that the variance of the model increases. So the model is doing worse and worse when having to predict new data, and to be general enough to capture new data with a good accuracy. But what do we do when we want the error of our prediction to be as low as possible? Now, to keep the final error of the model low, as with everything in life, the best solution is a trade-off. In this case, a trade-off between the bias and variance. To be precise, this is the relationship between bias and variance to the mean squared error. This is also called the Bias-Variance Decomposition. So the error decreases and decreases. But as soon as the prediction error starts to increase again, we can say that the model begins to overfit, or simply it has overfit. Practically, we can see this behavior as well when training, for example, a single decision tree with different depths. The deeper the tree, the more complex it gets, and the more complex patterns it can learn. We can then look at each success score for the training and testing data. And as expected, we can see that both training and testing scores increase. But at a certain point, the testing data begins to get worse again. Well, how can we fix this problem of overfitting? There are a lot of different approaches. One of the easiest being to add more data. The more data there is, the higher the data diversity will hopefully be. This can be done by just having more and diverse images, for example, or by augmenting, for example, rotating and slightly modifying the data you have, so that you can create a training dataset with higher volume and higher diversity. But there's so much more, from cross-validation to methods like bagging, which is used to improve the decision tree performance, keyword random forest, and then there is, for example, boosting and regularization and so on. But all of that is too much for this video. So, to summarize, when training a machine learning model, there is a risk that the model adapts way too hard to the data it is trained on, which might lead to the perfect results on the training data, but very bad results on the data that the model has never seen before. Mathematically speaking, we can describe this prediction error in terms of the Bias-Variance Decomposition. When the model gets too complex, one metric for that being, for example, the number of parameters it has, then the bias decreases a lot. This means the graph eventually perfectly fits the training data. On the other hand, with this increase in complexity, the variance of the model increases as well, meaning the graph is so weird that when new data has to be observed, the model's prediction has a high error. The prediction accuracy drops. The model overfits and it doesn't generalize well. So in this case, the sweet spot for a model is somewhere in between, where the bias might not be perfect, it might just be somewhat low, but so is the variance. I hope you could enjoy this video and learn something. If that was the case, please don't forget to like and subscribe. If you want to see more machine learning videos, here is my custom machine learning playlist that I have made for you and that you might enjoy as well. With that said, thank you very much for watching, and I will see you guys in the next one. Bye!